started. Welcome to this week's High Energy Seminar. Our first speaker today is Soumi. She's a PhD student at Syracuse University working with Professor Duncan Brown. And she's mainly interested in understanding the astrophysical information that we can get from binaries from gravitational wave measurements. She's also done quite a bit of work on common envelope evolution. Prior to her work at Syracuse, she got her master's at the University of Calcutta in India, and she got her bachelor's from St. Xavier's College in Kolkata, India. And today she's going to be telling us about the properties and evolution of neutron star and black hole binaries based on gravitational wave observations.
Okay, so I would thank all the organizers for this talk for organizing, and I would want to thank Morgan for actually hosting my visit, and I would want to thank everyone for actually coming here. So I'm going to talk about constraining the properties and evolution of neutron star and black hole binaries from gravitational wave observations. So the advanced LIGO and Virgo observatories have already observed a total of 10 binary black holes and 1 binary neutron star up till now. So it has actually opened up a whole new field of gravitational wave astronomy. And so now we are able to actually solve many open questions in astrophysics, which we were not able to earlier. So here is a plot from the catalog paper, which is put out by the Virgo and LIGO collaborations. And this plot shows the frequency versus time spectrograms for all the observed binary black holes up till now, so it's a total of 10. And then the reconstructed waveforms for each of these events. So at first I am going to talk about the areas of research related to the observations that I work on. So after you obtain the gravitational wave, if you analyze the data, it's actually possible to extract the parameters of the compact binary source. And the extraction of these parameters can be done by the traditional Bayesian parameter estimation methods. And I've been mainly spending a lot of time recently in this area of research. Another area of research which is related to the observations is the stellar evolution of these compact binaries and how these compact objects are actually evolving and are formed. And so one of the proposed channels of the compact binary formation is the common envelope phase. And I have been doing a project with Morgan in this area. So in a common envelope phase, it occurs when two stars in a binary, they evolve inside one common envelope. It starts occurring when one of the stars in the binary, it evolves out of its main sequence phase into a giant branch, and then it impinges upon the orbit of its companion and then engulfs it. And then the two stars, they interact via mass transfer, which occurs in between the primary into the secondary. And then at the end of this phase, if after the ejection of the envelope, if the two stars, they actually continue to stay as a binary system, then they can actually go on and form the compact binary sources for the advanced LIGO-Virgo. So in this project with Morgan, what we have been doing is performing hydrodynamical simulations to model the common envelope phase. So actually model the flow of the material around an embedded compact star in the envelope of the primary star. And then we apply our results from the hydro simulations to profiles from the stellar evolution codes, and then we try to study the evolution of the binary and the flow parameters over the common envelope in spiral. So I think that it's a great time to actually bridge this gap in between the two areas of research which I am currently working on. Okay, so now I am mainly going to talk about in more details about the part of my research which actually is based on the analysis of the gravitational wave data and the extraction of the parameters. So to give an overview of exactly how we go about this, so we read in the data from the gravitational wave observatories into our Bayesian inference pipeline, and the parameter estimation pipeline that I've been using in my research is called PyCBC Inference, which along with the external open source samplers such as the MC sampler, it is used to perform a Bayesian inference on the gravitational wave data by using Markov chain Monte Carlo techniques. And then what we get out of the pipeline are the measurements of the parameters of the black hole and the neutron star binaries, which are actually the compact sources of the gravitational waves in the data. So PyCBC Inference is a Bayesian inference toolkit inside the open source PyCBC software to which I have also been contributing. And the PyCBC software is mainly used in analyzing the gravitational wave data. And then we also have a methods paper which is specific to PyCBC Inference, and it explains the Bayesian inference framework and the methods we use and like how to use it. So you can use this code to do your own gravitational wave analysis using the open data. Oops. I don't have the equations coming up. Okay, I'm sorry about that. I'll just change to PDF. Oh, I'm really sorry about that. It was not showing up in in the other one. Yeah. Okay. So over here, I'm like actually highlight how we are actually performing the parameter estimation in the Bayesian formalism. So here is the Bayes theorem that you all know, and so over here, what we are doing is we are using the data D in order to measure the parameters theta of the gravitational waveform by actually matching the gravitational wave signal with a gravitational waveform model H. And the posterior is the one from which we actually get the estimates of the parameters. And the prior is the prior knowledge which we already have of these parameters theta before even analyzing the data. The data from the gravitational wave observatories, it enters into Bayes theorem via the likelihood, and the data in the gravitational wave detectors, it actually consists of the random noise in the gravitational wave detectors and any waveform that is actually present in the detectors. We assume that the data in the instruments are stationary and Gaussian. And so our model of the likelihood is actually the form of the likelihood of a waveform of well-known morphology in Gaussian noise. We compute a likelihood which is coherent by using the data from all the n number of detectors in the network. And the likelihood is mainly computed using a noise weighted inner product of the data minus the waveform template in the frequency domain. The evidence is mainly used when you are trying to compare between two analyses which have used two different models in order to infer which model is more preferred by the data. And the posterior distribution is usually mapped out by the external sampling algorithms of the pipeline, and all the estimates for the parameters theta is obtained by drawing independent samples from this posterior distribution. So when we are analyzing the gravitational waveform, the typical parameters that we are trying to extract are the component masses, the component spins, the luminosity distance, the source location and the orientation parameters, the coalescence time and phase. Also, in addition, if the components of the binary are neutron stars, then you can also extract other parameters from the waveform, like the tidal deformability parameters denoted by lambda 1 and lambda 2. And I'll be talking about these parameters in more details later in this talk. So we use PyCBC Inference to analyze the binary black holes from LIGO's first observing run. And here are the posteriors, a few posteriors from two of those events, GW150914 and GW151226. So here are the component mass posteriors on the right, and the effective spin parameter and the mass ratio parameter posteriors on the right, so the left and the right. So over here, all these gray histograms in 1D are the posterior distributions of the individual parameters after having actually marginalized over all the other parameters in the parameter space. And then all these lines on the top are the median and the 90% credible interval values. Then the 2D plots are showing the 2D histograms. So they are showing the it's showing a joint probability overall distribution of the two respective parameters after having marginalized over all the other parameters in the parameter space. And then overlaid on top are the 50% and 90% credible regions. So after doing our analysis, we had compared our posteriors with the posteriors which were obtained from the analysis of the LIGO-Virgo collaboration, and we plotted those in navy blue on top of ours. And then as you can see, they are in agreement with each other, which kind of validates our result out of our pipeline. So we have also released our posteriors in this repo in GitHub, and so it can be actually downloaded and used for other works. We have also released in this repository the run files and the configuration scripts which can be used to rerun our analysis. And it also contains a notebook which explains how to handle the data and to manipulate it. Then we use PyCBC Inference to also analyze the O2 binary black hole events, and here are the posteriors for 3 of those events. So the mass parameters, the effective spin and mass ratio parameters, and the inclination angle and the distance parameters. And we also released the posteriors for the O2 analysis in this repo. Okay, so for the remaining time of my talk, I'm going to mainly focus on the analysis of the binary neutron star event GW170817, which I did last year. So a few main differences in between this binary neutron star event and the binary black hole events are that it's possible to be observed across the electromagnetic spectrum, as you all know. And also there are matter effects that are involved in the binary neutron star systems, and so it's able to tell us about the nuclear equation of state. So here is a toy model of how the two neutron stars they orbit around each other. So as the two neutron stars are inspiraling around each other and are actually coming in close vicinity towards each other at the end of the inspiral, then the actual gravitational field of each of these neutron stars, it induces a deformation in the structure of its companion, and this deformation can we actually quantified by a parameter called the tidal deformability parameter, which we denote as lambda. And we can actually extract this parameter by analyzing the gravitational waveform in the data. So here is a time frequency spectrogram of GW170817. And the phase of this gravitational waveform, it can be thought of as that from a point particle model, so 2 point particles orbiting around each other, plus the tidal effects imposed on top of it. These tidal effects, they depend on the tidal deformability parameter, and the tidal effects can be computed using various methods like the post-Newtonian expansions, the effective one-body models, and the numerical relativity simulations. Then a combination of the component masses and the tidal deformability parameter, it can be used to express another tidal deformability parameter called the binary deformability. And this is the form in which the tidal deformability parameter enters into the phase of the gravitational waveform. And so this is the parameter that we've been trying to extract from the analysis of GW170817. And so this parameter can actually help us in probing the nuclear equation of state. So here is a plot from a paper from Ozell and Freer in 2016, and it shows a group of equation of state models that are proposed in nuclear physics. So these are the names of the equations of state. So each equation of state, it generates a specific mass radius curve on which the neutron stars would lie. So the equations of state which actually allow a higher radius are called the stiffer equations of state, and the ones which allow a smaller radius are called a softer equations of state. The tidal deformability parameter that I mentioned earlier, that is dependent on the mass, the radius, and the equation of state. And so this is how the tidal deformability is related to the equation of state. So here is a plot from our paper that we wrote in 2018, and it shows the variation of the tidal deformability with the component masses for thousands of simulated equations of state. And these have been performed by taking into account causality, the highest observed neutron star mass, and results from nuclear theory and experiments. So all the points in this plot which have the same radius are actually assigned a common color, and the mass range which we are interested in this plot is in between 1.1 and 1.6 solar mass, which is actually relevant to GW170817. So in this study, we found that in that mass range of interest, the tidal deformability actually varies as mass to the power of -6 and r to the power 6. So the tidal deformability, it goes as the beta to the power of -6, where beta is the compactness parameter, which goes as m over r. And so that allowed us to write this relation that the tidal deformability lambda is equals a beta to the power of -6, where where a is a constant, and we had calculated that value to be what is shown here. Also in that mass range of interest, we saw that for each equation of state, the variation of radius was very small. So as the two stars in the in our binary system is actually going to have the same equation of state, they are going to obey a common equation of state. So that allowed us to actually set that the radius of the two stars are approximately the same. So we set R1 equivalent to R2. So using this R1 equivalent to R2 constraint and the tidal deformability going as beta to the power of -6 relation, we were able to arrive at what we have been calling the common equation of state constraint, which allowed us to relate the tidal deformabilities, the component tidal deformabilities, via the mass ratio to the power of 6. Then we applied the tidal deformability going as beta to the power of -6 radiation and the R1 equivalent to R2 constraint on the equation for the binary deformability, which I showed earlier. And that actually helped us to express the common radius of the two stars, actually varying as the chirp mass and the binary deformability. And the chirp mass is a combination of the individual masses in the binary, and it is the most accurately measured parameter as it enters into the leading order term in the expression for the phase. So we used all the information from the nuclear matter study part of our work, and we did our parameter estimation analysis. In our analysis, we had fixed the source location and the luminosity distance parameters from the values obtained from the EM observations of this event, which is pointed to as by LIGO-Virgo. And then we applied our common equation of state constraint, and we carried out our analysis for 3 different choices of mass prior. So we used all total 3 different mass prior cases, as a few studies earlier to us, they had claimed that the choice of the mass prior can have an impact on the recovery of the tidal deformability. So the 3 mass prior cases we used were actually uniform distribution in between 1 and 2 solar masses, which is the mass range in which the neutron stars lie, and then a fit to all the observed neutron star masses in binary neutron stars in all the binary neutron stars systems in our galaxy, and then a fit to all the observed masses of the pulsars in our galaxy. And these 2 fits were obtained from the Ozell and Freer et al. Paper of 2016. And here is shown the posteriors for the main parameters of interest. So this is our chirp mass, then the mass ratio, then the individual component masses of the 2 stars, the effective spin parameter, and the binary deformability parameter. And you can see from here that the chirp mass is the most accurately measured parameter, the most constrained. And then our measurements of the mass ratio actually indicate that the BNS is more like an equal mass system, with the measurements of the mass ratio in between 0.7 and 1. And then we also measured very low spins, as it is expected that the neutron stars that are formed in the galactic field, they are not expected to have very high spins. Then what was more interesting is that we were able to combine the binary deformability posterior and the chirp mass posterior in order to obtain radius posteriors. So this is another plot from our paper which shows the binary deformability and the common radius posteriors. And so contrary to prior beliefs, you can see that the binary deformability is actually robust against the choice of the mass priors, with a peak at around 230, and we obtained a 90% upper limit at around 600. We were also able to measure a mean radius of 10.8 with a lower bound of 8.9 and an upper bound of 13.2. So I come back to the plot from the Ozell and Freer et al. Paper, which I showed earlier, and on top of that I have plotted the regions that are excluded by our analysis. So you can see that a few of the stiffer equations of state are already ruled out by this one particular event. And so it's actually interesting that how this only one event has been able to put constraints on the parameters which actually determine the structure and the composition of the neutron stars. And so we expect that with more events in the future, we'll be able to put more confident measurements of the tidal deformability and the radius parameters, and more tight constraints on the equation of state. So it brings me to the conclusions. So we have observed gravitational waves from a total of 10 binary black holes and 1 by neutron stars. And the analysis of all these events has been able to actually tell us about the properties of these compact binaries. And so we have been able to actually start looking at the populations of these sources. And these measurements also give us an opportunity to actually understand better all these channels of the compact binary formation and their evolution and composition. And we hope that with more detections in the future and with the upgrade of the current detectors and with more gravitational wave detectors added, we'll be able to solve many more puzzles in astrophysics. So that brings me to the end of my talk. Thank you for your attention.
Questions for sure?
Do you go back to the equation of state picture, like a couple slides back? Okay, that chartreuse colored one, isn't that impossible? I mean, it kind of slopes backwards here.
Like this one, you see?
Yeah, that one. I mean, it actually has a...
There's no reason you can't have an inverse mass radius relationship, right?
Really? Oh, it's for different masses. Oh, yes.
Yeah.
Okay. Sorry.
Yeah, so as the mass actually changes, so the Cayley deformabilities actually are related as the K2, which is the love number, and then R over m to the power of 5 relation. And we had seen that for the various ranges of masses, the K2, which is the K2 can have actually, at times it can go as a positive power of K2 of the mass, and at times it can actually go as an inverse power.
So those models are not necessarily stable.
That's right.
Other questions?
Yeah, I had a question about the BBH posteriors from O2.
Yes.
The slide on those. Ways back. Yeah.
This one is for O1.
Yeah.
Okay,
Yeah.
this one.
On the inclination plot, it looks like for some of the events, or the green event, we've been able to distinguish between a face-on and a face-off in spiral. What in the waveform gives you that ability? That's pretty tough to do, I would imagine. How do you distinguish a face-on versus a face-off binary in spiral?
Yes. So in these two cases, we can see that our observation has actually support for both face-on and face-off.
Yeah.
Whereas in this case, it has in the green case, it's more inclined towards a face-on as compared to the face-off.
Yeah. Is that for measuring polarization? So like right circularly versus left circularly polarized, or something else in the waveform?
It can be from the polarization. Yeah, it's a good question. Like it can be from the parameters and how the waveforms are coded up that we are not being able to make out in between if it's like face on or it's face off.
Yeah.
But it's a good question. Thank you for that.
That's the triple detection of Virgo, so it's always very impressive that we were able to distinguish the face on versus face off.
Okay, Soumi will be around both today and tomorrow, so if you're interested in talking to her, come up at the end of the seminar. Let's thank her again. And our next speaker is Charles Law. He's a grad student here at Harvard. He works primarily with Karen Oberg on all sorts of chemical complexity in different environments, young stellar objects, nearby galaxies, low-mass protostars. He was also an undergraduate here at Harvard, and in fact his thesis, which was on carbon chain molecules for embedded low-mass protostars, won multiple prizes, both in the department and the university at large. Today, though, he's going to be telling us about slightly different work, a project that he did looking at the kinematic evolution of an oxygen-rich supernova.
Okay, all right, great. Thank you for that introduction, and thanks everybody for coming, as well as to the organizers for giving me this chance to share this work with everybody. So I'm going to be talking about three-dimensional kinematic reconstruction of supernova remnant N132D. So I just want to point out that this was work that I had started about 2 or 3 years ago with Dan Milosavljevic, who's a postdoc here at the CFA and has now since moved to Purdue and is an assistant professor there, and as well as collaborators here at the CFA. So I'm sure everybody's seen sort of a slide like this representing, the stellar life of a massive star that grows, evolves, and eventually goes supernova and leaves behind some compact object. And so the question that I've been trying to answer with this project is to look at this phase, look at the supernova phase, and try to understand how the explosion is actually happening. So that question is, how do stars explode? There are various subclasses of supernova. Type 1As are very different than core collapse supernova. And today I'm primarily going to be talking about the core collapse variety. And so the question I want to ask is, what can we learn by constraining the explosion dynamics and the explosion geometries? And so this allows us to probe kinematic asymmetries that we see in the stellar ejecta that are not possible from extragalactic supernova observations. So if you look at close by supernova remnants, we can really pin down what is going on in the explosion as far as the stellar ejecta and whatever asymmetries and kinematic behavior we see. And so, as I said, the place to look for this is to look at supernova remnants. And supernova remnants represent ejected stellar interiors. So if you have a classic onion skin model of a massive star where you have various layers of nucleosynthesizing material, starting with hydrogen, going the whole way down to iron. Once this star goes supernova, core collapse supernova, and explodes, it will eject all of this stellar material out into the ISM. You'll end up with a remnant that looks something like this. It's Cas A, it's particularly young and close and very visually striking, where a lot of this material here was sitting inside the progenitor star at some point. So if you look at the different elemental morphologies of these supernova remnants, this is again Cas A, you can see that there is a fair amount of structure here. These are not perfectly spherical events. For example, if you look at the silicon and sulfur morphologies, they're tracing the periphery of the remnant here, tracing jet-like features, bubble-like features that you don't see if you look at something like iron, which is more compact and actually fills in some of these bubble-like features here. So these are not, this is X-ray observations here, and this is Spitzer, which is showing similar structure in various different elements. So these are certainly not spherical explosions. And observations have shown that, as well as hydrodynamical models, that these core collapse supernova are intrinsically asymmetrical. We've also seen from late-time optical spectra, there are multi-peaked emission lines, which are consistent with asymmetric, axisymmetric explosions. Particularly, it's been posited that these are consistent with torus-based explosions, where you have some internal extinction, which will be important when we talk about the structure of N132 in detail. There's also been spectropolarimetry studies that have shown asymmetries in the early explosion inter-ejecta layers. But overall, the origin of these asphericities that we see in the supernova explosions and we see prominently in the remnants is still uncertain. And so to go about answering this question, the best way to probe this in a direct fashion is to look at young, oxygen-rich supernova remnants. So oxygen-rich supernova remnants are a category of young remnants that have enhanced abundances of oxygen, neon, sulfur, typically with radial velocities of the ejecta that are expanding thousands of kilometers per second. And this material comprised the ejected stellar interiors from helium-burnt layers of massive stars. So they're really prime objects to study the explosion because we're looking at the ejected material from such an explosion. And they're ideal both for studying the evolution of massive stars as well as stellar nucleosynthesis. And so here's just sort of a postage stamp of four oxygen-rich supernova remnants. Cassiopeia A is the prototypical example in our own galaxy. Also, Pubis A and G292 are galactic examples. E102 here it resides in a small Magellanic Cloud. And the object I'm going to be talking about today, N132D, is in the LMC. So how can we actually go about doing this? So the reverse shock is the mechanism by which we can probe these ejected stellar material. In normal supernova remnants, optical emission arises from radiative shocks that are propagating into the ISM, and all of the stuff, all of the ejected material is typically fully thermalized and only accessible via X-ray observations. But in this rare class of supernova remnants, which is the oxygen-rich, the amount of CSM and ISM material that has been swept up is considered appreciably less than the ejected material. And so you have these clumps of ejecta that are closer to the center of explosion or expanding out ballistically. They are spectra and opticals characterized by an absence of hydrogen and helium emission lines and many heavy elements such as oxygen, calcium, sulfur. And these are the targets of the study today because those ejecta, which are ballistically expanding away, really carry a lot of information about the explosion and how it proceeded. So they give us a unique opportunity to peer directly into the ejected stellar material, and this material was deep within the progenitor star at one point. So by looking at this, we can really back out what was going on during the explosion. So the object of interest today is N132D. This is an oxygen-rich supernova remnant that's located in the Large Magellanic Cloud. It has a very distinctive horseshoe-shaped forward shock that you can see right here in X-ray with this large cavity here. The oxygen-rich nature of the remnant was discovered in the 60s by looking at the oxygen-3 lines. It was found to have an overall radial velocity range in excess of 4,000 kilometers per second. And the oxygen-rich material sits in a 12 parsec diameter ring right about here, whereas this larger forward shock that you see in X-ray extends quite a bit larger, 25, 30 parsecs. The proposed supernova progenitor was a type 1b core collapse supernova. And the suggested progenitor stars of oxygen, Wolf-Rayet, anywhere between 25 and 50 solar masses. And I just want to call your attention to the spread that you see in the supernova remnant age range, anywhere from 1,300 years, whole way in excess of 3,000 years. And the reason for this large uncertainty and for this large spread is because there are, unlike Cas A and unlike E102, there are no proper motion measurements taken of N132D. So all of these age estimates have been based on radial velocities, which have then been interpreted in terms of expansion. And so the age estimates are directly sensitive to assumptions you make about the morphological distribution of the oxygen-rich ejecta. And different authors in the literature have made different assumptions, different reconstruction methods, which has led to this scatter in the supernova remnant age. And so by better constraining them with the oxygen-rich morphology, we're also able to provide an updated and a refined age for this remnant. Just to provide a little more context to the environment in which N132D resides, it is bordered by these large molecular clouds. So to the south of the remnant, you see a large CO cloud right here, and you see a large H1 cloud as well, in which the forward shock and the X-ray emission in white here is basically carving out areas of these clouds. So there's definitely CSM, ISM interaction happening with the X-ray emitting material along the boundary of N132D. And this little spectra insert here is the author, Sano, actually analyzed the CO emission and found that there's definitely shocks affecting the gas here. So the initial efforts to map the three-dimensional structure of N132D started in the 1980s with an initial study by Lasker. This was using a 1.5 telescope, the CTIO. And the initial observations revealed a thin inclined ring that was due to an annular explosion around 2,000 kilometers per second. It's tilted about 45 degrees from the line of sight. And this is figures from this paper where each parcel here and number represents its radial velocity, again interpreted in terms of expansion. And this is an image that represents all of the oxygen-3 material. So this is all the oxygen-rich ejecta that's in excess of an absolute velocity value of 600 or more. So it's a bit hard to see the structure here, as you only have so many pixels. You see a little ring here that corresponds to this. But certainly in the intervening time, people have done better. So now what we know is that the oxygen-rich knots look something like this, where the X-ray contours here guide your eye for what the whole remnant's extent is. The oxygen-rich material is shown here in blue as these filamentary structures here. So it still sort of looks like the initial ring that we saw with last year's study, but there's a lot more structure here. All of this red material is hydrogen contaminated, so that would be CSM or ISM material that the ejecta have run into, so you can't uniquely determine sort of where that is in space. So basically, we just want to focus on the oxygen-rich blue material. The purple is so the purple. This right here is the X-ray emission, and when you get blue, which is oxygen-rich, on top of hydrogen-contaminated material, it just looks sort of purple. They just decided to plot it all on top of each other, which actually kind of makes it hard to see. But what the main result of this study done in 2010 was to make a three-dimensional reconstruction that greatly improved on last year's effort. So this is a stereoscopic map, not a true three-dimensional reconstruction, but nonetheless very visually striking. This was done with a 2.3 meter, so a lot better spectral and spatial resolution. And so there's some things that become immediately clear. And there's this torus ring-like structure that's broken up in several places, and it has fluffy material surrounding it, so it's not entirely a torus. It's inclined a bit to the line of sight, though they've adjusted it to make it easier to see. And so this was sort of the state of the art of three-dimensional reconstructions for N132D, this pioneering work that Voigt and Dopita did. But we wanted to push this further and make a better reconstruction in terms of spatial and spectral resolution, and go from a 2.3 meter up to a 6.5 meter. So I'm going to present the observations from Magellan. And so these were taken with the IMAX spectrograph and the Gizmo instrument. And Dan actually took these on New Year's, if you look at the dates. So he was there for New Year's Day when these observations were taken. And the idea was to use the oxygen-3 doublet to map the kinematics of these oxygen-rich knots. So that's looking at the 4959 and the 5007 angstrom lines. And the doublet nature of these lines will become important later for when we actually make the reconstruction. So what the slit map looked like was something like this, where you have, this is a little easier to see where the remnant is. The remnant is right in this region right here. And these long slit spectra were taken at every position here. So basically they were just moved 2.4 arc seconds all night long to cover as much of the spatial extent of the remnant as was possible, to pick up as much oxygen-rich material as we could. So here's to provide some broader context to the remnant itself. So this structure that we're seeing, if you look back at the Hubble image here, it's this U shape here, which is called Lasker's bowl, discovered initially by Lasker in the 80s, and that exhibits a curved inner boundary, like a classical bow shock material. And it's particularly hydrogen-rich, so it's most likely existing ISM material that's been shocked by the supernova remnant. So we're not particularly interested in structures like this. Instead, we're interested in things that are oxygen-rich and free of hydrogen. So that's these turquoise filaments, which are a lot less spatially extended than, say, this forward shock material here or Lasker's bowl. And again, this is the forward shock, so this is the full extent of the remnant. And so then the way to identify true oxygen-rich ejecta, things we can uniquely associate with the ballistic expansion away from the center of explosion of the supernova, are done via our spectral investigation. So we just look at something like here. We take its spectra. We see that it is hydrogen-rich in the form of a strong H-beta emission line. It does have oxygen-3 doublet present, but the fact that it has this strong hydrogen emission, we can't necessarily claim that it's basically not been freely expanding. It's hit hydrogen, it's interacting with hydrogen, it's been decelerated, and we're not going to take something like this to be considered a true oxygen-rich knot. Whereas if you look somewhere in the middle along this turquoise material, you see an ejecta knot which is free from H-beta emission, which is entirely oxygen-3 doublet, And in this case, you see 3 distinct kinematic components here. And to be able to determine these velocity components and to be able to make the 3-dimensional reconstruction, we start with something like this as far as raw data, where this is north and this is the dispersion axis. And we're particularly interested in this stuff right here, this clumpy, fast-moving knots that you see in the oxygen-3 doublet. So it's a lot of kinematic structure that we want to go through and extract for each position. So for each position across this way, that's an RA and a DEC, and we extract 1D spectra. And once we extract the 1D spectra, we see something like this, free from hydrogen, just purely oxygen-rich. And then we cross-correlate with a template of the doublet. We know the theoretical ratio between this line, the first line of the doublet, and the second line, which is a 3-to-1 ratio. And then we just move across the spectra and are able to, for each RA and DEC position, so for each one-dimensional spectra, we're able to extract several or as many radial velocity components, kinematic components as exist there. And so doing this in detail, doing this across the remnant and across all of those slits that I showed in the previous slide, we get something that looks like this. So it's important to note that we surveyed a large area of this remnant, but the oxygen-rich knots really are only within this section right here. So we're not detecting lots of other pure oxygen-rich material way out here or here. They're really almost all confined to this smaller spatial extent quite near the explosion center. And so to just show this in context of what was been previously known as far as these oxygen-rich knots, this was work done by Morse in the 90s, where they introduced this this nomenclature where R is redshifted knot, and B is a blue shifted knot. And so we just adopted the same nomenclature to show consistency with their results. We're able to fill in some of the material that they weren't able to detect here. But overall, we reproduce the expected morphology of the knots very well. This is also quite consistent with what Voigt and Doppler have found, where now it's just plotting the oxygen-rich knots that they used for their stereoscopic 3-dimensional reconstruction. So what do the full data look like for us? If you look at in terms of RA, DEC, and radial velocity, you see something like this, where the dominant kinematic component is shown here. So you see one side is prominently blue shifted, and you get red shifted material here, as well as this spatially separated runaway knot of oxygen-rich material. So these are the true bona fide real oxygen-rich knots that we're going to use for our 3-dimensional reconstruction. It's about a little over 4,000 individual points extracted from the 1D spectra. And almost all of them come from this main shell of ejecta here, and only a tiny bit from the runaway knot. We assume a center of explosion, which is needed to actually make 3-dimensional reconstruction, to be this star right here, which is taken from the Morse paper, which fit the oxygen-rich distribution in the most symmetric way possible. And then to actually make the 3-dimensional reconstruction, as I said earlier, we're going to assume a ballistic trajectory, that these oxygen-rich knots have been traveling unimpeded and undecelerated from the center of explosion. And then we're going to fit a spherical expansion model. So that is just basically assume that the explosion intrinsically was going to explode in as spherical as possible to get a conversion factor, basically to be able to convert this RA and these DEC values into true velocity space. And once we do that, we can fit the projected velocity versus the Doppler velocity we measure, and we fit a semicircle model to that and end up finding a conversion factor of 96 kilometers per second per arc second. So every arc second away you are from the assumed center of explosion, you're going to multiply by this 96 kilometers per second. So you can do this for all of the 4,000 points that we measured. And what you end up is making a reconstruction that looks something like this. So this is showing various viewpoints of the 3-dimensional model, where now we're entirely in velocity space. The blue arrow here is to the observer, to Earth. So if you looked along that blue line, you would see the plane of sky in knots, that we were showing in the previous slide. And then this is to the east in orange and to the north in green. And so we recovered the torus morphology quite well. So this is looking at the plane of the torus. There is a bit of distortion, as we'd expect from the Voigt and Dopita paper. We see the runaway knot, which is spatially disconnected from the remnant. The sphere here is shown to guide your eye. It's about 1,700 kilometers per second, which was the radius we fit in the semicircle model. And so if we show this in various projections, we can really get a handle on what this torus looks like here, or what this ring looks like here. You can see that there are prominent gaps here, which is not just due to our sampling. This is an intrinsic a lack of emission in these particular areas. And if you see in 3D, if you do these projections, if you look along the x and the y, you recover exactly what you would expect to see in the plane of the sky, because this was just a proxy for RA and DEC right here. So what do we observe? So we see a tilted ring or a torus morphology. We see more blue shifted material than red shifted, overall by about 340 kilometers per second. By doing this, we're able to provide an updated remnant age. So we find 2,400 years or so, which is quite consistent with the Voigt paper's result, which found 2,500. So the age estimates for this remnant are somewhat converging now to be around 2,500 years, which is a good sign. So to characterize this better, as I noted that this is somewhat of a torus-shaped distribution, torus-shaped geometry. We decided to fit a torus model to this. And so that's what's shown here, with just various viewing angles. This is along the side of the torus. These are looking down on top of it, where the red points represent things that can be very well fitted and very well constrained by a torus. The green triangles here are more diffuse, fluffy material that's not as well fit, that sits asymmetrically on one side of the torus. And the runaway knot is shown right here. And again, where the blue vector here corresponds to the line of sight, like you'd see it on the sky. And the black arrows here correspond to the plane of the fitted torus, where all the points have now been shifted into the plane of the torus just for visual clarity. And so this torus is defined as to contain 75% of the main shell ejecta, just to account for the fact that there's this fluffy material that could never realistically be fit by a torus unless you increase the minor radius so much that it would not really physically be meaningful. As you see in projection, we find a minor radius of around 1,000 kilometers per second, and that seems to visually make sense with the torus that we're seeing here. So overall, we find an inclination of about 28 degrees with a line of sight. We see that this runaway knot is nearly perpendicular, 89 degrees from the plane of the torus. And we're able to really well constrain the ejecta here with a torus. So some takeaways that we can get from this three-dimensional reconstruction. A natural thing to do is compare with Cas A, because that's a prototypical oxygen-rich supernova remnant, particularly well studied, and has good three-dimensional morphology from previous efforts. And so here's something interesting that we noticed, that Cas A is known to have sort of be cut off along its rear-facing ejecta, along a sharp boundary line. And this has been interpreted in the past as the Cas A ejecta running into inhomogeneous material in the ISM and just expansion not being allowed to happen along this axis but being free to happen here. But it's interesting that we see something somewhat similar for N132D, though you would not necessarily expect that with, if this wasn't intrinsically related to the explosion dynamics of the star. And furthermore, if you look at the distribution of the Cas A, you see a torus-like structure as well, just similar to what we see in N132D. And so that, again, points to potentially something that's intrinsic to the stellar explosion, that there is maybe a somewhat thick ring and dense material around an initially rotating star that then you're seeing as a torus once the explosion happens. So this is, again, is providing some evidence for the fact that torus structures are common in core collapse supernovae, and the fact that maybe the intrinsic explosion really sets the geometry more than previously thought. And Cas A is known to have these bubbles, nickel bubbles, which have been interpreted either as pistons, basically explosion pistons that are coming from the iron material, or alternatively from radioactive heating. But they're pretty prominent in the three-dimensional reconstruction of Cas A. Here you can see these bubble-like features. So we also wanted to just check to see if we could see anything similar superimposed on the torus feature for N132D. And one point to note is that it's substantially harder to do this because N132D is an order of magnitude older than Cas A. Cas A is only about 350 years old. And so any small scale asymmetries like the rings are going to be much better preserved. Whereas in something like N132D, they're most likely to be very smoothed out and very hard to see. But nonetheless, it's intriguing that we have this fluffy, non-toroidal material. They're just highlighting here. It possibly serves as an analog to these bubbles at Cas A, although it is much harder to claim that you're seeing something as very spherical and ring-like as here because of the advanced age of N132D. And the last point I want to focus on about the reconstruction was the presence of this runaway knot, this spatially disconnected point right here. And as a result of being so far away, once you do this reconstruction, it ends up having a total space velocity that's nearly 2 times that of the bulk ejecta. So it's moving very fast, and it's at a nearly perpendicular to the torus plane, which makes you think something immediately about a bipolar explosion, potentially, or a jet at least. And what's more interesting is that it's coincidental with an X-ray enhancement. So this is showing X-ray contours at N132D. And the runaway knot that we see in opticals right here. And there's an X-ray, nearly X-ray point source right below that. And this is a pure oxygen-rich knot. We don't see any hydrogen there, so that's a good sign. If we look at the X-ray and zoom in on this runaway knot, or the enhancement that we see that's close to the runaway knot, we see a small delay, a small offset, which is consistent with the X-ray optical brightening effects that we've seen before. Displacements of a few arc seconds have been seen in Cas A, likely due to a highly inhomogeneous ejecta. So these are still very likely to be physically associated with each other. And this runaway knot is particularly enhanced in silicon material. It's at least twice the abundance of the LMC, and it's also elevated to the main shell of N132D. So this is just looking at the X-ray spectra, zooming in on seeing the silicon-enhanced features. And this is particularly interesting because if we compare this to Cas A, if we look at the known northeast jet right here and the counter jet to the southwest, which is shown right here, this is a silicon knot. This really starting to look like an analog for these Cas A jets, that this is really material that was deep within the progenitor star and that it managed to push its way out during the explosion and is now moving very quickly, very far away, and very chemically and kinematically distinct from the main shell of ejecta. And this has also been seen or hinted at in other supernova remnants. Vela, in particular, has these 2 shrapnel pieces of material, A and G, which are silicon enhanced. And you can see both of them quite well. This is a Rosat image. This has been studied with XMM Newton to discover their silicon-rich nature. And lastly, that we've been able to reproduce this with 3D hydrodynamical simulations. If you introduce velocity and density and homogeneities in your exploding star, you're able to have these silicon jets protruding out. Here it's shown in green. So overall, this is just, to place this in larger context, there's been a recent study that found around a third of core collapse supernova have some sort of asymmetries like this. They call them ears, but just sort of asymmetries that potentially represent jets. And so it's the fact that we find this silicon-enhanced jet or feature in N132D means that jets might be participating in the core collapse supernova mechanism in some at least reasonable fraction of supernova explosions. And so overall, I just want to end on the summary. So we have made a new reconstruction of N132D, show that it's an inclined torus surrounded by some diffuse non-toroidal material, which with hints of similar morphological similarities to Cassiopeia A. We're able to confirm the presence of this oxygen-rich runaway knot that was also seen in the Voigt and Dapita paper, but we're also able to show that it's consistent with this X-ray point source. It's enhanced in silicon, and it has similarities to these other jet-like features that we've seen in other remnants. So it makes it suggestive, and it makes it very interesting as sort of a follow-up to study this. And there are upcoming X-ray observations, an accepted 1 megasecond Chandra observations that are going to be taken of N132D. So that will certainly help clarify the X-ray morphology of the remnant. An additional IR and optical follow-up can help characterize this runaway knot more thoroughly, as well as potentially find others, because this was substantially faint in the oxygen. It's interesting because of its location and its chemical makeup, but it was very faint. So if we look sort of on the outskirts of the remnant, it's possible with deep optical observations we could find more of these runaway knots of oxygen-rich material, which really help tell us about the explosion. Either if we find more, that means something, or if we don't find any more, that really will help us pin down what happened during the N132D explosion. Right. Thank you for listening.
Questions for Charles?
So at the beginning when you introduced the event, you said it was a catchy effect from the event. How do you classify?
You need light echoes to do it well, and they don't exist for this supernova. So that's where there's a question mark there. So we don't actually know. And there's been people trying to pin down progenitor types and masses, but that's still highly uncertain in that you still have a range. But
Jet formation and jets flowing out of the event, I think it's much harder for not to be stripped.
yeah, but it's still, that is highly uncertain. So that's sort of the question mark is there. Yeah, we don't know for sure, and it'll be hard without light echo measurements.
About less than 2 months after the explosion of 1987A, a blob was detected moving with a fraction of the speed of the light, 10.000. Just after the explosion, so to say, and was followed about 6 months after that with speculum spectrometry. Asymmetry was also detected in that direction, and it was followed a couple of years later. One of the interpretations subsequent theoretical papers gave was that it was a jet, or part of the core jet. If you look at the papers that came 87, 88, 89, and then the references.
Okay, that's particularly interesting.
Because that's
Thank
the
you.
closest to morphologies.
Yeah, that is interesting. Great, thank you.
One last question.
Were you able to get a better handle on the gauge by tracing back the velocity measurements?
Yes. So
you get something close to
you get 2,400 years, which, I mean, the Voided during their reconstruction found 2,500 years, so it's sort of, that really is sort of converging on an age now, because the initial values, the initial spread was from earlier studies, say in the 90s, when people were saying the maximal age could be 3,000, minimal age could be like 1,000, but now I think we're converging, because we have a better handle, 2 independent studies at least that have done it relatively good spatial resolution to say this is actually the sort of distribution, that this torus feature is real, and that we've really confirmed a lot of the things that have been done before.
For those who have more questions, Charles is here, so I encourage you to get in touch with him. Let's thank both our speakers again.